Okay, formal definition of context-free languages. So, since you don't have enough tuples in your life, a context-free grammar is a fourth tuple. It has variables, terminals, productions, and starting variable. Okay, and in the beginning, first time you see it, it's very bizarre, but once you get used to it, it's in fact pretty natural. So we have a set of variables, and we have a set of terminals t, which just think about it as the alphabet. And then we have a set of production rule, where a production rule is just, you can think about it, the rule of translation that says a variable, a single variable, can be translated into a string alpha. Importantly, the string alpha is not just from t, it can contain both variables and terminals. Right? So you can have both things. And then a start symbol is just one of the variable, which is the root of your derivation. And this doesn't make much sense without an example, so let's do an example. So let's start maybe from the most basic context-free grammar that is interesting. So we have only a single variable, which is s. The terminals are a and b. And now we have the following derivation rule. S can go to epsilon, so if we have the variable s, we can generate epsilon. If we have a, s can generate a, s can generate b, and here is the more interesting bizarro rule. S can generate the string ASA, right? And similarly, S can generate BSB, right? So we write it, this collection of rules, derivation rule is written in this more compact way here, where we used the OR notation, right? So this really says, if you zoom into it, says S can either go to epsilon, A, B, etc. Okay. And now let's think what we can do with it, right? So S is the start symbol, so that's what we have initially. And then we ask ourselves, what can we derive from S, right? So we can take the first derivation rule, the first production, and generate epsilon. So that's one thing we can do, which is not especially interesting. And similarly, we can generate A, the string A, and the string B. The more interesting things we can generate is, for example, ASA. Right? Now, if we generated ASA, then we cannot quite finish because there are still variables in the string. So the rule of the game with CFGs is that as long as your string contains the variables, you need to keep deriving. You need to keep applying production rules. So now I'm going to use, for example, the rule that S goes to BSB. So this is going to be A, and that's going to be the inner part, B, S, B, A, right? And we can continue in this fashion, right? I can do, take the middle S here, so now I have A, B, and I can put the middle S, now I can derive it into, let's say, A, S, A, B, A, right? And we continue in this fashion. In this specific grammar, we always are going to have only one variable, S, somewhere in the middle. And, in this case, we will get ABA, ABA, if I use the derivation S goes to epsilon. Okay? Abba, Abba, which in Hebrew is father, father. Okay. Now I have also a pre-arranged example, so let's see it here. So this just uses the rule going to be repeatedly. So this is Abba, Baba, I hope I'm pronouncing it correctly. So what strings are generated by this grammar? And if you think about it a bit, the first letter and the last letter in the generated string are generated by the same rule, either this rule or this rule, right? This was also generated by the same one, and this was generated by the same one, and so on. Which means that the ith letter from the beginning in the final string is equal to the ith last letter in the generated string, which means that this is a palindrome. Okay, and palindrome are of course not context-free. The language of all palindromes, even over A, B, sorry, they are context-free, but they are not regular, right? So palindrome, the language of palindrome is not regular, but it's definitely context-free. I just showed you a grammar for it. Here is the more formal definition in tuple form, so that you can fill up your cup of tuples. Here are some examples of palindromes for fun. I guess the one most relevant for today is person, man, woman, camera, TV. Sorry, I meant a man, plan, sorry, a man, a plan, a canal, Panama. That sounds like relevant 100 years ago, or 150. Okay, so palindromes are context-free grammar, and you already, this already shows the power of this tool over regular languages. Right? So we already get a richer family of languages, which is good. Okay, here's another example, which was our canonical example of non-regular languages. The language of 0 to the n, 1 to the n, right? So this is very easy to derive because, well, first we derive epsilon, and then, we say we need to count 0 as 1, right? And that's it. That's the grammar of this language, if you think about it. It's a very short grammar. And what really is going on is that we are counting, whenever we generate a 0, we also generate a matching 1. That's why it's really counting the numbers of 0s and 1, and that's why it generates this language. Okay. Now there is some convention about the notation. You don't need to worry about it that much, but let me just mention it because it makes life easier. So characters are, small letters. Variables, we use capital letters. And the rest of the notation doesn't matter that much, but there is some stuff. Okay, now to really define the language formally, we need to speak about this derivation idea, right? So I give you two strings, right? Those two strings are mixed string, right? They have both alpha 1 and alpha 2, and they have both variables and terminals, right? And we say that alpha 1 derives alpha 2, which we, use this bizarro arrow to notate by this grammar, but you can just use a regular arrow. This is just for fun. If there is alpha 1 contains some variable inside it, in this case a, and we apply one of the production rule of a to replace it by gamma, right? So this is one step of the derivation, right? So in this case, for example, if we look at the previous grammar, right, we get that S derives epsilon, right, and so on and so forth, right? Every step of derivation, every step of using a single production is essentially a derivation. You do one derivation, and of course we want to do it repeatedly. So we're going to define it now, the Kate derivation, which is alpha 1 arrow k to the alpha k, alpha 1 derive k to, we write k on the arrow. If what happened is that we have k strings such that alpha 1, And okay, I guess here we are using slightly different notation. So we have alpha 1 k derive alpha 2. If we can derive from alpha 1, we can derive beta 1. And from beta 1, we can derive alpha 2 with k minus 1 steps. It's an inductive definition. Okay. And alternatively, you could just say that alpha 1 k derive alpha 2 if you can derive from alpha 1 a string beta 1 in k minus 1 step, and then from beta 1 you can derive alpha 2 in 1 step. Okay, and of course we don't really care about k most times, so we will do arrow star to say that it's derivable, right? There is a sequence of derivation such that you can generate this string. Okay. Now you have to realize that context-free grammars can be quite tricky because you might be able to go into infinite loop that don't generate anything. So usually we will want grammars that are not very friendly to loops. We will talk about normal form later on, but that's it as far as derivation. Okay, now we can define formally what is a context-free language. A context-free language is given a grammar G, which we just defined, is all the string that can be derived from the start symbol with any number of derivation steps. Okay. And such a language is context-free language or context-free, CFL, if it's generated by the context-free grammar. Okay. So the same thing are the same, right? We either speak about the language of the grammar or the language without the grammar, if there exists a grammar that generated, but the two things are essentially equivalent. So let's see some examples. So 0 to the n, 1 to the n we already seen, so we don't need to do it again. This was this, right? Just the simple grammar. Maybe here a slightly more interesting example. 0 to the n, 1 to the m, where m is larger equal to, m is strictly larger than n, right? So let me create a grammar for it where t would be t1 or z1, right? And z would just goes to, oops, sorry, complicated things, t1 or s1, okay? Where s is the rule before, s goes to epsilon or s goes to 0, s1, okay? And the start symbol is t. This is the start symbol. Stop. Okay, so my claim is that this grammar generates this language. Let's see why. Well, I can apply the production t goes to t1 as many times as I want to create a suffix of ones. And then when I get fed up with it, I derive the rule from t to go to s. This adds another one. And s generates, of course, this 0 and 1 to the n. Right? So we get 0 to the n, 1 to the n. This is the derivation from s. And then we're going to get a sequence of 1 that was generated independently, which is the language n. And of course, I put here the rule s1 because we require that n would be strictly larger than n. So that's the way to guarantee this. Okay, the next one is another important example, and this is the balanced parenthesis language, right? So this is, for example, a valid expression, a valid string in this language. Oh, this one. Okay. So how do we generate this as context-free grammar? So the basic observation is that we have two things that we can do, right? Either we break our string into two parts, where both of them are balanced, or alternatively, the whole expression start and end with an outer parenthesis, and the inner part is also balanced, right? So it's essentially a recursive definition, right? So S, let's see, either goes to epsilon, because everything should go to epsilon if it want to, and either it goes to S, open parenthesis, close parenthesis, which just is equivalent to taking the string and putting outer parentheses on it, or alternatively SS, right? This just says take two balanced parentheses expression and concatenate them, right? So this is the context-free grammar for this. And this is it.